Friends, so far we have discussed about the analysis of continuous beams with sinking of support. Now we will study some of the problems on both sinking of the supports and rotation of the support. Here in this problem, support A rotates by 0.002 radians in clockwise order and support B sinks by 5 mm and C sinks by 2 mm. Take the flexural rigidity EI equals 18 into 10 to the power of 3 kilonewton meter square. Analyze the beam by using the slope deflection method. Here this one is A, this is fixed. B, this is simple support. C, simple support. D is simple support. A to B is 4 meter and moment of inertia is 2I. B to C, the moment of inertia is 4I and the length is 8 meter. C to D, the length is 3 meter and moment of inertia is I. Here, first we have to find out the rotation and sinking of the various supports with respect to their original position. Here, with respect to original position of this support A, this is rotated by 0.002 radians in clockwise direction, hence theta A equals 0.002 radians, that is in clockwise direction. Then support B, with respect to its original position, it is the sinking is or settlement of this support is 5 mm in downward direction. Here with respect to support at A, B is in downward direction. As per our sign convention, this one is negative, that is positive, that is delta is positive. Or if you observe the rotation here with respect to this span, with respect to its original position, this span is rotated in clockwise direction, hence delta equals 5 mm, that is positive. Or if you convert that into meters, 0.005 meters. Similarly, next support B is rotated by 5 mm with respect to its original position. B is there is a settlement of 5 mm in downward direction with respect to its original position. C is there is a settlement of support C in downward direction, that is 2 mm. Then if you draw a horizontal line, this vertical intercept or vertical ordinate at this point, that is 5 minus 2, then that one is 3. Here with respect to B, C is at higher level, hence this one is minus 3 mm or minus 0.003 meters. Then at C, or here by observing the rotation, the rotation is anti-clockwise, hence this one is negative. Or with respect to this support B, C is at higher level, then this one is negative. Similarly, here C sinks by 2 mm with respect to its original position. Here D is at higher level, then delta 3 for this span CD is minus 2 mm or 0.002 meters, that is negative. Or if you observe the rotation, that is anti-clockwise. Then the first step is calculate the fixed end moments due to load. Here there are no loads on any span AB, BC or CD, hence no loads, hence no fixed end moments, or the fixed end moments in all the spans are 0. Then the second step is, after knowing the settlement and rotation at the various supports, then we have to write the slope deflection equation for AB, BC and CD. 2 equations for AB, 2 equations for BC, 2 equations for CD, one from near end, one from the far end. Here MEB equals, that is here theta A, that is with respect to its original position, it is rotated in clockwise direction by 0.002 radians, that is clockwise, hence MEB equals 2E, the moment of inertia is 2I and the length is 4 meter. Then this one equals, that is 2E into 2I by 4 inside of the bracket. Here we are writing from A, hence 2 theta A, that is 2 times near end plus 1 times far end, that is theta B, minus 3 delta by L. Delta 1 is for this span, that is 0.005 millimeter. Length of AB is 4 meter. Then the fixed end moment is 0 by substituting the values of EI, that is 2 into 0.002 into 18 into 10 to the power of 3 divided by 4 get cancels, that is here we'll get this is 2 into 0.02 into 0.002 into 18 into 10 to the power of 3 theta A. Similarly 2 into 2 by 4, that is 4 get cancelled, 18 into 10 to the power of 3, that is EI into theta B, minus 18 into 10 to the power of 3 into 3 into delta divided by 4. After simplification you will get the equation, that is 18,000 theta B plus 4.5. This one is equation number 1. This is the slope deflection equation for the first span. Then similarly write the slope deflection equation from the other end, that is MBA equals 2E into 2I divided by 4 inside of the bracket 2 theta B plus theta A minus 3 delta by L. That one is here 3 delta by L plus close the bracket plus MFBA, that is by substituting the values 2 into 18 into 10 to the power of 3 divided by 4 inside of the bracket, that is 2 times near end, that is 2 theta B plus 0.002, that is theta A, minus 3 into 0.005, that is delta, divided by length of AB is 4 meter. Then after simplification you will get 36,000 theta B minus 31.5, that is equation number 2. Now we can write the equation for the slope deflection equation for MBC, that is 2E, the moment of inertia is 4I, the length is 8 meter inside the bracket. Here we are writing from B, that is 2 times theta B, that is 2 times near end slope 2 theta B plus 1 times the far end slope, that is theta C, minus 3. Here delta for this one is, that is minus 0.003 meters, minus 3 into inside of the bracket minus 0.003 divided by length of BC is 8 meter. Then after simplification we will get 36,000 theta B plus 18,000 theta C plus 20.25. This is equation number 3. Similarly from the other end, that is MCB, by substituting the values, that is 2 into 4 into 18,000, that is EI divided by L, that is 18. Then here 2 times near end slope, that is 2 times theta C, here we are writing from C, that is 2 theta C plus 1 times far end slope, that is theta B, minus 3 inside of the bracket, that is delta, that is minus 0.003 meter divided by 8. By closing this bracket plus fixed end moment is already it is 0 because there are no external loads. Then after simplification this one is 36,000 theta C plus 18,000 theta B plus 20.25. that one is equation number 4. Now we can write the slope deflection equation in the same way for the last span, that is MCD. That one is here MCD equals, here by observing this, that is MCD, that one is here that is 2E, the moment of inertia is I and the length is 3 meter. Then 2E I divided by 3 inside of the bracket, here we are writing from C, the near end slope is 2 theta C plus the 1 times far end slope, that is theta D, minus 3 times inside of the bracket the delta for this one is 2 millimeter, that is negative, or minus 0.002 divided by 3. Then by closing the bracket the fixed end moment is 0. Therefore after simplification we will get 24,000 theta C plus 24,000 theta C plus 12,000 theta D plus 24. Here this one is equation number 5. Then similarly we can write one more equation from the opposite end, that is from D, that is from the last support, that is 2 into EI 18,000 divided by L, that is 3 inside of the bracket. Here we are writing from the end D, hence that is 2 theta D, that is 2 times near end slope, plus 1 times far end slope, that is 1 theta C, minus 3 delta. 3 delta is minus 0.002 divided by L, that is 3 meter. Then this one becomes 24,000 theta D plus 12,000 theta C plus 24. This one is equation number 6. Here we have written 6 equations, 2 for each span, for AB 2, for BC 2, for CD 2 equations. Now we can apply the equilibrium condition. Here in this, at B there are 2 members are connected, one is BA, one is BC, hence the summation of the moments at this point is 0. That is, at B summation of MB equals 0, that give us MBA plus MBC equals 0. Since there are 2 members are connected at B, one is MBA, one is MBC. By adding those two, we will get, after simplification, that is 72,000 theta B plus 18,000 theta C, that one equals 11.25. Here we will get one simultaneous equation. Then here there are 3 unknowns, B, theta B, theta C, theta D are 3 unknowns. We must get 3 equations, 3 simultaneous equations. Similarly, at C, there are 2 members are connected. One is CB, one is CD. Hence, the summation of the moments at this joint C equals 0. Therefore, summation of MC equals 0. 2 members, that is CB is 1, CD is 1, that is MCB plus MCD, that we have already written. That is equation number 4 and 5. By adding those two, here we will get that equals 0. That is, by adding those two, 18,000 theta B plus 36,000 theta C plus 12,000 theta D, that one equals minus 44.25. Here this one is simultaneous equation number 2. Then at the end support, if the end support is provided with the simple support or roller support or hinged support like this, here the support is simple support, hence the final moment at this end is 0. Here at fixed end, the moment is not equal to 0. Moment is not equal to 0. But if the support is provided with either the roller or hinge or simple support, the end moment is, the moment at that end is 0. Therefore, at D, MDC equals 0. That is, by equation number 6, that is 12,000 theta C plus 24,000 theta D minus, that equals minus 24. Here you have got 3 simultaneous equations. To solve these 3 equations, by solving equation 1, 2, 3 for theta B, theta C, theta D, we will get the values of theta B equals 3.33 into 10 to the power of minus 4. Theta C equals minus 7.08 into 10 to the power of minus 4. Similarly, theta D equals minus 6.46 into 10 to the power of minus 4. Now, after getting the values of the slopes at B, C and D, they are the unknowns. Here the in slope deflection equation, either the slopes are unknowns or the deflections are unknown. Here theta B, theta C are the unknowns. By substituting the values of theta B, theta C and theta D to get the final moments. Hence, by substituting the values in the above slope deflection equation, that is 1 to 6, that is, we will get MEB equals, that is 10.49 kilonewton meter. That one is positive. That means that is clockwise. That one is clockwise. That is 10.449. Similarly, MBA equals, that is, by substituting the values in the second equation, we will get, that is, MBA equals minus 19.51. Minus means that is anti-clockwise. Then MBC, By substituting the values of theta b and theta c in equation number 3, we will get mbc equals, that is 19.50, that is positive, that means that is clockwise. Similarly, by substituting the value of theta c and theta b in equation number 4, that is mcb equals 0.76 kilonewton meter, that is positive, that means that indicates that is in clockwise direction. That one is in clockwise direction. That one is clockwise. Then similarly, by substituting the values of theta c and theta d in equation number 5, that is mcd equals minus 0.74 kilonewton meter, that means that is minus means that one is anti-clockwise. Then mdc, that is the end support is on the simple support, mdc equals 0. You please verify by substituting the values of theta d and theta c in the above equation number 6 to get whether it is 0 or not, maybe a fraction, or it is nearly equal to 0. If the difference is more, then you have to recalculate. Here, after knowing the values of the bending moment, here we can draw the bending moment diagram. Here the moment MAB, that is clockwise, that one is clockwise, that one is clockwise. Similarly MBA, that one is anti-clockwise, that one is anti-clockwise. MBC, that is clockwise. MCB, that one is MCB, that one is clockwise. MCD, that one is anti-clockwise. MDC, that one is 0, that one is 0, no moment at that end. Now we can draw the moment diagram, bending moment diagram. Here no simply supported beam bending moments, because the spans AB, BC, CD, they are not subjected to any load. Simply draw the support moment diagram. Here, by observing the span AB, in span AB, both the moments MEB and MBA, both bending moments are sagging bending moment. They are sagging bending moment. Hence, here first draw the datum line or reference line. With respect to this datum line, so far we have shown the sagging moments in upward direction, that is, and sagging moment in downward direction. Here this one is the ordinate of the bending moment at A, that is 10.49. Similarly at B, the bending moment is 19.51. By joining these two lines, here this one is join the line, that is 10.49, 19.51 kilonewton meter. These are the bending moments. These are the positive or sagging bending moments. Hence I have written positive sign. Here this one is sagging bending moment. Then here by observing this, here at this end the bending moment is, that is hogging. Hence this one is negative bending moment diagram. I have shown the ordinate above the reference line, for this one. And then again MCD, that is 0.75 kilonewton meter, that is hogging. Here the ordinate of the bending moment is 0.75 and ordinate at this point is 0. That is, here these two moments are, this moment diagram is negative bending moment and this one is positive bending moment. Now we can draw the elastic curve for this. Here in this portion the slope is 0 at this end. Here to draw the elastic curve, this one is the elastic curve. Here the support B sinks. Here this is positive bending moment. This is positive bending moment up to this point. Here there is one point of contraflexure where the bending moment changes from positive to negative. Here the bending moment up to some point, here up to this point, that is positive. Then the moment curvature is, that is, it is like this. concave upward. Concave upward as shown in figure. Then from in between B and C, it is again negative bending moment up to D. Then the curvature is, that is, convex upward like this in portion up to in between B and C. Then up to end D, the curvature is like this. That is, the curvature is concave upward. Then to draw this one is the elastic curve for this beam, that is elastic curve. Here this one is the elastic curve for this diagram. This one is the point of contraflexure. Here there is only one point of contraflexure where the bending moment changes from positive to negative. This one is the elastic curve. It is like this. This one is end A. This one is support B. This one is support C. This one is the end D. This one is end D. Here it is like this. This is the elastic curve for the above problem. Then we want to draw the shear force diagram for this one. Here this one is phi A, this one is phi A, this one is phi A, and this one is phi B, this one is phi A, this one is phi B, this one is Vc, this one is Vd. Here by closing this portion, that is here by closing this one is here, this one is phi A, this one is Vb, this one is Vc, this one is Vd. Here if you close the portion, that is to take the to calculate summation of, by applying the equilibrium equations one by one, that is summation of phi equals 0. Here Va we can assume Va, Vb, Vc all are upward in direction. Therefore Va is upward, Vb is upward, Vc is upward, then Vd is also upward. Then here first calculate Va plus Vb plus Vc plus Vd equals 0. Here to calculate the values of the support reaction, here first we have to consider this portion, that is summation of the, by taking the moments of all the forces about B, that is Va into 4, that one is clockwise since we have assumed this in upward direction. This 10.49 is also positive. Va into 4 plus 10.49, this one is minus 19.51, that is Va into 4 plus 10.49 minus 19.51, that equals 0. Therefore Va equals 2.25 kilonewton. This one is Va equals 2.25 kilonewton. Then go to the next, that is at C. Here closing this portion only we will consider the right side of C. Then here there is a reaction Vd. Then this one, the moment here, this one is anti-clockwise, this one is also anti-clockwise. Vd into 3, that is the distance is 3 meter, that is minus Vd into 3. This one is also anti-clockwise, that is minus 0.76. Therefore Vd equals minus 2.25 kilonewton, that is downward. That one is acting in downward direction. here that one is Vd, that one is 0.25 kilonewton. Then here now again by taking the moments of all the forces about B, that is by closing remaining portion, that is here by considering the forces to the RHS of B. Here just now we have calculated Vd. Vc is one of the unknown that we are going to calculate, that is we have assumed it in upward direction, that is Vc into distance is 8 meter, that one is anti-clockwise. Then 0.25, that is Vd into 8 plus 3 total distance, that is clockwise, that one is clockwise, plus here the sum of these two moments equals 0, that is one is clockwise, one is anti-clockwise, and then here there is a clockwise moment at the support, that is 19.50. then the summation of these equals 0, therefore Vc equals 2.78 kilonewton, that is positive, that means that is upward. Then by substituting the value of Va, Vd and Vc by equation 1, we will get, that is Vb equals minus 4.78 by this equation, that is by this equation number 1. Then we will get Vb equals minus 4.78, that means Vb equals 4.78 in downward direction. Now we have got the values of Va, Vb, Vc and Vd. This one is downward, that is 4.78 kilonewton. Here this one is Vc, that one is 2.78 kilonewton. Now we have got the values of the support reactions Va, Vb, Vc. Then start from the left hand. Va is 2.25, that is upward. As per your sign convention, left upward is positive, that is upward, that is positive, hence that is 2.25. Here in between A to B no loads, then the shear force remains constant, that is 2.25 kilonewton, that is positive. Here this one is the reference line or datum line. With respect to this reference line, we have taken 2.25 kilonewton ordinate in upward direction, that is shear force at A. This point is A, this point is B. At support at B, there is a support reaction Vb equals, that is 4.78 in downward direction, hence the shear force becomes, that is 2.25 minus 4.78. That is the support reaction is 4.78 in downward direction. The shear force is 2.53 from this point to this point, that remains constant, that is for 2.53 kilonewton, that is negative. Here in between B and C no reactions. At C there is a support reaction, that is in upward direction, hence minus 2.53 plus 2.78, that is there is a upward reaction Vc, then the shear force becomes 0.25 kilonewton, that is positive. Then that remains same from C to D. Again there is a support reaction at D, that is downward, hence minus 0.2 plus 2.25 minus 0.25, that one becomes 0. Here the variation of the shear force is like this. This one is the shear force diagram for the above problem. Here it completes with this problem. We will continue in the next video.